tonight is going to be, the previous Kosmica was about film. So we presented two short films and one film. And tonight is going to be, the topic is going to be sound and the possibilities of sound in space, including how do you record sound in space? Is there sound in space, which is a big discussion. Some people assume that it's just a vacuum, so there cannot be any kind of sounds. However, we'll discuss that today. Also, the signification of electromagnetic waves and what some artists are doing with all this data. So, to start with, I would like to introduce Harger. She is the director of the Lighthouse, originally from New Zealand. She's been working through this collective, this name, Radio Qualia, together with Adam Hyde. And she's been working in different projects with radio astronomy and more things. So, I let Honor tell us more about her work. Yes.
Wait, before I start, can you hear me without the microphone?
Yeah.
No.
I was going to try and do that without the microphone, but so if I run out of hands, I'll apologise in advance. Firstly, big thanks to Nicola and Rob and Nahum for having me here. It's a real pleasure to be here amongst friends and colleagues and even some of the artists that I'm going to talk about. So that's wonderful. Just a wee bit about me first. So I'm a curator, and at the moment I run Lighthouse, which is a digital culture agency based in Brighton. And what we try and do is work with artists and filmmakers and technologists on everything from exhibitions through to productions and events. And what our mission is to really try and show that digital culture is about more than just tools and technologies. What we're really interested in is the emotion and the aesthetics, and about trying to perceive the societal transformations that is being brought about by the ubiquity of digital technology. And not just digital technology, but perhaps kind of the softer side of technology too. So I have to mention our project done in collaboration with the Arts Catalyst, which was very much about the kind of bio, soft and wet side of technology. As well as doing that, I'm also an occasional artist. I'm really going to refer to that a little bit today because I'm going to talk about the work of proper artists, and I don't want to confuse myself with them. But I also run a blog at Particle Decelerator, and that's really about bringing together, I guess, what I call kind of particles of research about physics and cosmology and where that touches art and culture. So I'm really operating at the kind of interstices for the purposes of tonight's conversation between art and science. And I guess one of the ways that that's manifested in my work over the past few years is an investigation into what Pythagoras, and then Kepler after him, referred to as the music of the spheres. And so I guess kind of in homage to Kepler and Pythagoras and the many scientists and engineers and artists who came after them, I'm going to sort of try and attempt to do a little bit of a homage, an ode, if you want, to some of the people who helped bring those musical spheres closer to us here on Earth. So I'm going to talk to you about how we've used sound to learn about space. And I think we all have a very good idea about what space looks like, right? You know, we've all sort of seen images of space. In fact, they're kind of all around us. From the sort of speculative images of space that we see from science fiction, to the inspirational visions of space that were given by artists, to these increasingly spectacular images that we're able to see of space enabled by new technologies. Love this one. It's Jupiter. And that's Saturn, rings of Saturn. But though we have an overwhelmingly strong visual understanding of space, in popular culture at least, we don't really have an understanding of what space sounds like. And indeed, you know, for very good, right and proper scientific reasons, most people associate space with silence. Yet the story of how how we came to understand the universe is just as much a story of listening as it is of looking. But despite this, very few people have ever heard space. Hardly any of us could describe the sound of a single planet or star. So just to kind of correct that for tonight's evening, this is the sun, or it would be, because you hear any sound, which we don't. No sound. In the distant universe. This is a pulsar. This is one of the slower ones. They get up to what's known as millisecond pulsars, which we hear as pure tones, but that's one of the ones that we can kind of really understand from a sonic perspective. So my research and artistic practice is all about listening to these weird and wonderful noises emitted by what I think are the magnificent celestial bodies that make up our universe. And lots of people ask me, well, you know, why are we, you know, kind of listening to space? What are we actually learning from this, other than having sort of slightly odd encounters with noise? And I guess, you know, kind of what I would answer that it's through listening that we've discovered some of the universe's most extraordinary secrets. We've learnt its scale, we've learnt what it's made of, and we've even learnt how old it is. So this evening, I'm going to tell you a short story about how accidental encounters with strange noises have taught us some of the most important things that we know about space. And we need to kind of locate the story somewhere. So the kind of physical environment that we're locating this story is within the invisible landscape that is the electromagnetic spectrum, and specifically the radio part of the spectrum. And that's where most of my work as an artist has taken place. And despite the fact we can't see it, it is indeed a real physical manifestation, a real ecology, which has, as the quote says, its own physical contours. So our story isn't going to start, weirdly enough, for Kosmica, which is often very much rooted in, you know, kind of exciting science fiction understandings of space and rockets and futuristic spacecrafts. It's not going to start there, sort of perhaps a little bit disappointingly. It's going to start with a very humble technology. And in fact, the very medium that's kick-started the revolution that's enabled our computers and our mobile phones to be here, and that's the telephone. So we're going to hear a lot of bells this evening. Bell is a recurring theme over the evening. So it's 1876, and this is Alexander Graham Bell, and he and Thomas Watson are working in Boston on the development of the telephone. And a key component of Watson and Bell's setup was a half-mile-long telephone line that ran across the rooftops of several houses in Boston where they were working. And the line carried the telephone signal that would later make Bell a household name. But as the kind of proto-scientists or real scientists in the room will know, like any long length of charged wire, it also became an antenna. So Thomas Watson used to spend hours listening to mysterious crackles, whistles and pops, which his accidental antenna detected. Sounded a bit like this. Now, the reason why this was interesting is because antennas didn't exist when this accidental antenna was invented. It was years before Heinrich Hertz had proved the existence of radio waves, significantly before Nikola Tesla's four-tune circuit, the inventor of radio, arguably. We can have that conversation another day. Long before Marconi's first broadcast, at least 20 years before that. So Watson wasn't hearing radio signals from us because we didn't have the technology to transmit. And until Watson and Bell had accidentally built an antenna, we didn't have the technology to receive either. So what were these strange noises? Well, Watson was dialed in, that's Watson dialed in there, sort of slightly literal graphic, to the very low frequency radio emissions caused by nature. And some of these crackles and pops that you can hear here had quite kind of prosaic explanations. They were lightning, kind of atmospheric disturbances. But these eerie whistles and these curiously melodious crackles and chirps had a rather more exotic origin. Using the very first telephone, Watson was in fact dialed into the heavens. He actually guessed that these sounds that he was listening to on the telephone, literally, were caused by activity on the sun's surface, which was a quite extraordinary piece of intuition because there was absolutely nothing within physical science at that time that could have led him to believe this. And he was right. It was the solar wind interacting with the Earth's ionosphere that he could hear. So whilst inventing the technology that would usher in the telecommunications revolution, Watson had inadvertently discovered that the sun emits powerful radio waves, and he accidentally became the first person to listen to the sun. So it's the sun that's the beginning of our story, and it really is an apt place to start. The solar wind that Watson was listening to is caused by the sun constantly emitting and ejecting immense energy into space in the form of solar flares and coronal mass ejections. And when they reach our planet's surface, these energized particles interact with our ionosphere and they create phenomena such as the aurora. And the aurora often carries with it this special type of radio wave, very low frequency radio waves, or VLF waves, which Watson had heard on his telephone headset 140 years ago. And VLF radio is really important to our story because VLF waves occur in the same frequency as human hearing. Whereas the sound historian Douglas Kahn puts it much better than me, and he's to credit for that Watson anecdote. VLF being very long waves, once received on the antenna, they end up in the human audible range without having to be transposed. Now, it's really important to kind of clarify at this point, they're not sound waves, right? They are light waves. They're electromagnetic waves in the radio spectrum. So, as Doug says, we have to resort to technology, radio technology, in order to hear them, because we don't have antennas on our heads. We've got these weird, pressure-sensitive sensory organs instead. Although he does note that if our hearing apparatus, for instance, were a little bit different, so if, for instance, our thousands of cochlear hairs were growing externally on our skin, rather than these weird two-ocean seashells sunk into our heads, that we might be able to detect electrical waves, much like some other animals can, for instance sharks, but we can't. So that's where the artists come in. And this is one of, I think, one of the most interesting practitioners working with VLF. This is the Australian artist Joyce Hinterding, and she's been building radio antenna to listen to VLF waves for well over 20 years. Her antenna sculptures are often absolutely immense. She transforms entire galleries into vast antenna waves. So we're looking here at the work that she did for us at the Rejvadi Gallery in Sunderland, which was a version of aeriology, and here's 4 other examples of aeriology where you've got around 26 to 30 kilometres of copper cable, which is wound around the physical architecture of a building, and then is used as a gigantic antenna to collect electromagnetic energy in the VLF range. Really extraordinary work. This is a little bit more modest. These are smaller handmade VLF antenna. This is part of the EarthStar installation, which basically kind of sensorializes the sun in 3 different ways, one of them in sound. And these VLF antenna are specifically sensitive to radio bursts emitted by the sun. And they're plugged into a standard amplifier. You can actually see the amplifier here. So this is kind of getting to the heart of what Doug was talking about how we don't need to transpose this technology. The antenna is just literally plugged into the PA. There's no radio in between. And what we can hear is a combination of signals from the sun intermeshed with our local electromagnetic environment. A little bit similarly, but quite differently, this is 20 hertz, which Lighthouse co-commissioned for our Invisible Fields exhibition. And this is a depiction of a magnetic storm, which is happening in the Earth's upper atmosphere, caused again by the sun's interaction with the ionosphere. And the sound we can hear is VLF radio waves. They'll start to become familiar. You're going to hear them quite a bit tonight, I think. And these were captured by a Canadian facility called Charisma. And they're converted into audio. Same kind of technique, literally just plugging, kind of the antennas into a kind of sound card in this case. So what you can hear is the sound of the sun interacting with the earth. And what Semiconductor have done to create the visuals is visualize the sound. So you're kind of seeing the sound there. The sound almost is a kind of series of particles. Those of you who know about early sound technology and know about Chladni plates and kind of vibrational energy of kind of particles will probably find this quite familiar. So moving along. So Bell and Watson's accidental discovery of radio waves from the sun, which they listened to through their early prototype telephones, started us on our journey. But let's just jump back in time again and find out what happened next. So it's 1932. It's 50 years on from the original invention of the telephone. And Watson and Bell's telephone has really completely transformed global communications. But Watson and Bell's revolution was a global one, and that meant tackling the vast geography of the globe. So going from slinging lengths of wire across the rooftops of a few houses in Boston to laying cables across the seabed of the Atlantic Ocean was really quite a big transition in terms of technological infrastructure, as I'm sure you can probably imagine. And before long, Bell Telephone Labs, as they were then, the new research wing of Bell's commercial operation, was looking to new technologies to help them optimize the new revolution. So radio could carry sound without wires, so this could make the whole thing a hell of a lot cheaper. No need for those undersea cables, very expensive, really difficult to lay, particularly with the World War, on the horizon. But radio was really annoying. The medium's really lossy, it still is now, and there's loads of sources of interference and noise, so not so good for the telephone. So what Bell did was they hired a radio engineer to work out exactly what all of these noises were. Because the thinking would be, if they could identify all of the noises, then there must be a way that they could find a way of eliminating them, kind of build a hardware codec, if you want, to kind of get rid of them. So here he is, the radio engineer, and most of the noises that this intrepid young engineer, who some of you may recognise as Karl Jansky, investigated, really turned out to be quite kind of common, sort of easily identifiable noises. So they were caused by lightning, by cars backfiring, by the very many electrical sources which had started to kind of pervade modern life in 1932. So he nailed most of them really quite quickly. He was quite a smart engineer. But there was one noise that he really couldn't identify, and it drove him a bit crazy. particularly because it seemed to be appearing in his headset 4 minutes earlier each day. Now, any amateur astronomer of any ilk knows that this is the call sign of something that doesn't originate from Earth. And this is dreadfully unsettling, because this is not meant to happen. I mean, there wasn't meant to be, radio that came from anywhere but Earth. Watson's discovery at this point, remember, wasn't a discovery. It was an intuition. But it appeared, Yancey couldn't find any other explanation for this, so he surmised that the noise was indeed cosmic radiation, which came from the centre of the Milky Way. And he basically, went public with this. So this is the front page of the New York Times from May 1933. Front page news, not very common that happens these days, unless it's got the word Higgs in it. He had indeed made a historic discovery, and that's that celestial bodies could emit radio waves as well as light waves. So 50 years after Watson had spent hours listening to what actually, had turned out to be the sun, Jansky's careful listening had ushered in a whole new age of space exploration, the radio astronomy age. Over the next few years, radio astronomers connected up their antennas to speakers and learned about Jupiter, the sun, and other objects in the radio sky by listening. And interestingly, for the first 20 years of radio astronomy, the science was driven not by high-tech labs like Bell or science facilities like Oxford, but by amateurs. And they were the pioneers that mapped the radio sky. Amateurs rather like this. This is Thomas Ashcraft. And he's photographed here in our Invisible Fields exhibition in Barcelona earlier this year. And he's an artist and an amateur radio astronomer. He's based in New Mexico, and he studies objects in the night sky with both optical and radio telescopes. He's interested in both. You can see some of his setups here. This is some of his antennas. He's become very well regarded in the scientific community for his methodical observation of phenomena like solar flares, Jovian storms, which we heard a bit earlier on, and meteor encounters. And this is one of his observations of a solar flare, not much better than the one that we recorded, actually. Much better at what he does. And what I really love about what Thomas does is he has a very poetic interpretation of both his visual and his auditory observations, and it really recalls Watson's own initial encounters with the cosmos and his quite beautiful descriptions of what he was hearing. But it also brings to mind Douglas Kahn's observations about the limitations of our own bodies when it comes to detecting electromagnetic energies from space. And Ashcraft really kind of brings that home, because he describes himself as a new type of artist, an electroreceptor. And he thinks of himself as possibly, a sort of a new invention of a kind of artistic mode, or maybe the reinvention of something which has existed since ancient times. And his job as an artist, in the same way that a painter's job is to paint, is to receive. And he kind of puts it quite explicitly here, where he says that he considers his antennas, very reminiscent here of Marshall McLuhan, as an extension of his nervous system. And so this poetic and scientific foldback is all over Thomas's work. It's very beautiful, and we're listening now to a piece that he created called Time Dilation Experiments, which is made using astronomical data. But as Thomas says, it was definitely inspired by Solaris, by Tarkovsky. So, he's not trying to be realistic here. He's become something of an expert in observing phenomena called transient luminous events, or TLEs. And TLEs are extraordinary, very poorly understood. They're electromagnetic pulses that occur in the upper atmosphere. And they've got really delightfully evocative names. So this is a blue jet. We also have species of TLEs called gnomes, elves, and sprites. I'm not making this up. And Thomas's observations of TLEs are being used by NASA and other science institutes to help them better understand these phenomena. He's really considered a bit of a frontline experimenter in this field. So here we've got an artist whose practice is positively contributing to science. And this is a science that took something of a giant leap forward in the next chapter of our story. And to tell it, we have to return, of course, to Bell. So it's 1964 now, and we're back at Bell Labs, and this time we're at Holmdel, which is just outside New Jersey. And it's almost 30 years after Yansky, and in a strange historical echo, two scientists are also having a problem with noise. So here they are, this is Arno Penzias and Robert Wilson, and they're using the horn antenna at Bell Labs Holmdel Laboratory to study the Milky Way, the precise thing that Yansky discovered, radio waves from the Milky Way. And their antenna was pretty much the most cutting-edge observational instrument in the world at the time within radio astronomy, and it enabled them to detect signals from the galaxy with really extraordinary precision. They were listening to the solar system in high fidelity. But there was a bit of a glitch in this high fidelity soundtrack. There was once again a mysterious persistent noise which was disrupting their research. The noise was in the microwave range, and it seemed to be coming from all directions simultaneously. Now this was really annoying, that just isn't possible. So they assumed it must be a glitch with the dish itself, and quite famously they assumed that it must be something to do with all the pigeons that were nesting inside the dish, who surely kind of must have had something to do with this interference. So they cleaned the dish, removed all the pigeon droppings, assumed that the noise would go away, but it didn't go away. And what it turned out to be, this mysterious noise, was the oldest and most significant sound that anyone had ever heard. It was cosmic radiation that has survived from the birth of the universe. It was the first experimental evidence that the Big Bang existed, and the universe was born at a definite moment, some 13.75 billion years ago. And so our story returns to the beginning of all things, the Big Bang. This is the noise that Penzias and Wilson heard, the oldest sound you're ever going to hear, the cosmic microwave background radiation from the Big Bang. But our story doesn't end here. Because in arriving at the beginning, we're taken back to the beginning of our own story, which is the sun. The eminent solar physicist Lucy Green recently described our sun, rather aptly for our story, as a resonant bell. She was explaining the immense pressure waves that build up in the centre of the sun, which are episodically released and can be detected rather like peals of vast cosmic bells. She was referring to the modern branch of astrophysics known as helioseismology, which studies the actual sound waves which resonate through blazing hot gases inside objects like the sun. And we study many stars using this method, and so the wider field is called astroseismology. And this provides a different vector for us to be able to experience the space as sound. So when we're using the helioseismology vector, this is what the sun sounds like, really quite different than before. And you have to sort of imagine a vast sound wave rippling through the core of the sun. This is a sort of really bad artistic impression of that, causing it to oscillate, causing the plasmas of the sun to oscillate, and we can experience these effects as sound. And so that brings us to our final part of the story, and our final artist, Caroline Devine, who's here. So it's really awkward speaking about her work right here. Her recent work, 5-minute oscillations of the sun, uses both the sound waves we can detect through helioseismology and the VLF waves that we experienced earlier in the work of Watson, Hinting, and Semiconductor. The work was a site-specific installation sited within the dome, a dome structure in Milton Keynes, and Caroline can talk to you more about that. And it oscillated between what she refers to as an acoustic mode, which uses the helioseismology data, and an electromagnetic mode, which uses the VLF recordings. For the helioseismology component, Caroline worked with the research facility BISON, and that's a network of 6 remote solar observatories and sort of remote monitoring solar, who monitor solar oscillations. And that's operated by the School of Physics and Astronomy at the University of Birmingham. So let's listen to a very short clip of Caroline's work, because I don't want to say too much about it because she's here. So I think as with Joyce's work and Thomas Ashcraft's work, Caroline's really employing quite rigorous methodologies and tools within science, but creating a really quite poetically charged sensory experience. And all of these artists, in my view, are opening up the vast hidden dimensions of space to our ears, and perhaps doing so, bringing space a little bit closer to us here on Earth. So thanks very much.
Hello. Yeah. Well, thank you so much, Honor. We have like 10 minutes for questions and answers. So, who's the first one?
If anyone wants to ask Caroline any words, just
What? Over there. We need to use the microphone because we're live streaming this, so people can hear.
Honor, thank you very much. Great to hear you talk about all of that. There's one thing that I wanted to ask, and I'm sure there'll be a few of us who've also got this question. Right at the beginning, you were playing us the sound of the Sun and Jupiter and various things like this. It's not actually sound itself, is it? Is it? It's not. It's transparent.
No, it's not. It's the radio waves which are audified, and so what audification means, as opposed to sonification or amplification, is that you're taking an electromagnetic wave and you're turning it into a sound wave, and that's what the technology of radio does. So a radio receiver does exactly that. You know, kind of when you hook it up to an antenna, the antenna will detect the electromagnetic wave, the radio wave. The radio receiver will, if you want, kind of decode it, try and work out what it is. And inside the radio receiver, you've got an amplifier that will, you know, kind of help turn this electrical signal into sound. So there is no sound that propagates through space because space is a vacuum. So, you know, you can't, you know, sound doesn't have any medium to travel through. So we can have sound inside, you know, energetic objects like stars, discovered relatively recently, but they can't really get out with a star because as soon as, you know, kind of let you leave the gaseous atmosphere of a star, there's no medium for the sound to travel in, and mechanical waves require a medium.
Yeah, thanks. I just wanted that to be cleared up for everyone.
Thanks, Kat. Anyone else?
Can I ask a question?
Yes.
Hi, just off the back of that question that Kath asked. So if the radio waves are taken into something equivalent to a radio receiver, is it just like using a regular radio receiver?
Yep.
So it's the same kind of interpretation as any other radio waves that we use for our radio broadcasts.
Exactly, and that's why we got really interested in it from an artistic perspective, because the Sun and Jupiter are particularly resonant in that case, because they're very good at broadcasting in the exact frequency ranges that we use for our terrestrial broadcasts here on Earth, particularly in the shortwave bands. So a lot of that noise that you're hearing when you're listening to shortwave, I don't know if anyone listens to shortwave anymore. If you follow Test Match Special, you probably do. But if you're looking for Test Match Special and you're hearing noise, a lot of that's the Sun. Not all of it, but a good percentage of that, kind of hissing sound in between the stations on a shortwave radio receiver is caused by interference from the Sun. Probably not Jupiter, because you wouldn't have a big enough antenna. But if Jupiter's having a particularly stormy day, then maybe some of that's Jupiter too. It's the same frequency range, 20 hertz. 20 megahertz, sorry.
Thank you.
Thank you.
There's one over here.
Okay.
Yeah, there's a question related to wires, really. If you're using long-distance telephone cables under the sea, is that a means of picking up these sounds or translating these sounds?
Well, you could, wires are really good as transportation mechanisms. So I always find that, kind of wires are much more reliable of getting a thing from point A to point B than the air is. It's a lot less lossy. But as far as I understand, but I'm not an expert in this regard, the undersea cables that we're using right now for everything, that's the internet down there, those undersea cables, are not particularly conductive these days. I mean, the reason why Watson's long line of cable tossed across the houses in Boston became an immediate antenna and could pick up, kind of direct ionospheric sounds, kind of radio waves turned into sound, is because there was nothing else kind of transmitting, because we weren't creating any interference at that point. But we are now, so it's much more difficult to, kind of build an antenna and get it to detect something kind of precise than it was back in 1876. So as far as I know, but then there's probably engineers in the room that are more knowledgeable about this than me, undersea cables are not picking up, kind of interference.
And can I just ask you about the last piece, because you mentioned that the shape of the building was used in the sound. Sorry.
Yeah, it was a parabolic dome structure, because I was looking specifically for a space that would amplify those time sounds, and parabolas work brilliantly doing that, because they can focus sound and amplify it at the centre. And yeah, so that it was a site-specific piece, and it was chosen in order to amplify the VLF, and the tones were put throughout it as well. So yeah, it was sort of used as a kind of like a giant instrument in a way.
Yeah. Thank you.
Hi. Yeah. Is there kind of any aspirations to transmit sound the other way into space?
That's very controversial. There's you would have heard of SETI, so that's the search for terrestrial intelligence. There's another thing which has been debated extremely vigorously within the radio astronomy community for years, called METI, which is active SETI, or messages to extraterrestrials. And there are you know, kind of, there are varying points of view about, you know, kind of whether or not this is a good idea. You know, kind of some of the scientific community think that, why not? Let's give it a try. We've got really powerful radio telescopes like Arecibo that can, you know, kind of be both transmitters and receivers. So, you know, kind of let's just send the most powerful signal that we can into space and see what happens. There are other people that think that that could cause Independence Day. So it would be a bit bad idea because that would cause an alien invasion. And these are real, proper, sophisticated kind of like debates which are happening within the sort of the radio astronomical science community. So yes, it does happen, and many telescopes have a dual function. They can transmit and receive.
I have a related question, quick one. How close are we to becoming a silent planet in the last 10 years as digitalisation takes away from transmission?
It's getting worse, Rob. It's becoming.
We're getting louder.
Yeah, we're getting way louder. Okay. So the number of radio silent zones, which you know kind of are required for radio astronomy, are you know kind of becoming less and less. So you know they're becoming endangered spaces. And we saw that really clearly quite recently, where one of the big science projects of the 21st century is the construction of something called the SKA, the Square Kilometre Array. And this will be, if you want, the new LHC. And it's going to be an array of, you know, kind of around 1,000 radio telescopes that are going to be constructed across a vast area that are all networked together that, you know, kind of make a super radio telescope that will network up with all the other radio telescopes and make a radio telescope the size of the planet. So a big science project. And the problem with the bids, the international bids to site the SKA somewhere was finding radio quiet zones that weren't, if you want, kind of destroyed by interference, mainly from mobile phones. Because mobile phones operate in the same frequency that a lot of really useful radio astronomical research happens in. And the whole thing about the world going digital is a complete misnomer, because digital is either using the deep sea cables that we kind of put down in the 1930s, or it's using the air, you know, kind of like, so digital's only compounded the problem, you know.
Yeah. As with visual information that we have about outer space, there's some aspect that I suppose you could call objective data that we get, but there has to be some point at which there's interpretation and then reinterpretation. And I'm wondering, with the artists that you work with, what, or perhaps for the artist that's here, what the thinking is that goes into the sort of human element of reinterpreting this.
Well, every artist is different, so I'll just speak from my own perspective here. The reason why Radio Kwali and my artist group, who you know kind of recorded those sounds that we heard early on, or collected them, the reason why we were really interested in those sounds is because we felt they were as close as we could get, with all the caveats, you know, kind of in place about these being, you know, kind of electromagnetic waves turned into sound waves. They were as close as we could get to the kind of real energy that was coming from these objects. So the only human interpretation involved was the, you know, kind of the sort of the building of the radio receiver. You know, kind of that's it. You know, kind of there was no other, you know, kind of, if you want, kind of artistic intervention. But what you're going to hear in the next couple of presentations are, you know, kind of much more nuanced, you know, kind of, I think, kind of artistically, you know, kind of careful decisions about how to interpret those sounds and musicalize them. And I think Caroline's work, you know, kind of particularly with the helioseismology data, was very much a, you know, kind of an attempt to kind of take the data and then, you know, kind of compose with it.
Great, I think that's it. Okay, Caroline.
Would there be any plans for Radio Kwali to go back live again or be available again?
Well, yeah, I mean, I sort of feel a little bit fraudulent talking to you about this stuff because our own project, Radio Astronomy, was archived in 2008. So it's quite old. So we'd love to, but it's just about, you know, kind of time and resources and, you know, balancing our practice with our day jobs and, you know, kind of all of the other things that we do. So maybe, you know, if someone comes and helps us.
Yes, Radio Qualia was a great project. Get it going again.
There you go. Honor, thank you so much for coming tonight.